All right. So is it? Okay, so it's 9:30. So let's get started. So I guess you get a moment to read the comic since we didn't get it quite up. But a couple things is now we have some graders that are aboard on the course. So I posted a note about that on the piazza. So Muyang Song, Diraj, and Krishna. So the graders have joined the course. They're just getting up to speed now. But essentially their main role, their main interaction with them will be through grading interviews for every homework project. So I'll be sort of posting details about signing up and doing that for the homework projects in the next day or two. So just like I said in the piazza. Okay, let's see. So other couple announcements I would think, I think it's just a reminder that, post questions on the piazza rather than, say, emailing me or something like this. I mean, this hasn't really happened, but I just, as a reminder that, I think you probably have noticed that you've gotten responses when you've posted publicly from students much faster than I've been able to. I certainly check the piazza all the time and trying to provide responses, but there's a lot of sort of expertise in this room with differing background, as we know from the first day. And so if you post publicly, then you can get, lots of good information. There's an option to post anonymously if you want. Of course, we won't know if you're posting if it's anonymous, but remember, it's really, we've taken the oath, right? So we're all good, right? The piazza is sort of an extension of this classroom. So since we've all taken the oath, right, we're not going to judge each other. That we're all here to help and support each other in the learning, right? But, that option is available. Okay, so, certainly I think questions like, how do I link with the runtime? These are questions that, you're going to face or come across or something like that. These are totally questions that you can ask. Or even what's been asked already, like, hey, where's the submission site? Okay, so as far as submissions, just a clarification, also repeating from what was on the piazza, is that everyone should submit at least one copy. This will just help us, administratively know, if you've submitted your homework, right? So you could test with one person's account if you want, n times, and then, make sure just each to submit your own so we have a record of that. Any questions on that, those logistics? Drew?
Can you explain the pair programming and how that should work with remote students? And
yes.
My partner is remote, so how we're supposed to pair program and submit and everything else?
So it is, the intended idea of the pair programming is to be able to have a close collaborator. And if you're a remote student, I imagine that you might be more calling each other up and using things like Skype and screen sharing and things like that to collaborate. That's totally fine. As far as pair programming goes, it's not that you have to have the same code, although you are also welcome to. You will sort of go into the kind of the grading interviews together as a pair. So it's sort of like you should have a good understanding of each other's code if it's not even the same code. Okay. Right. And of course, you're welcome to collaborate in larger groups. I just want to make sure that everyone has at least one partner or one partner in crime, to be able to go to with whatever details they have about their compilers and their understanding. Now, of course, this is a graduate senior level course / master's level course, so I expect you will get what you need from the project, right? It's the learning device, the main learning device for the course, so make sure that you understand every bit of it in that implementation. So I really strongly encourage pair programming, which is everyone understands every line of code and is working on every line of code. Maybe you often sort of actually program together where you're sort of where one person is typing, the other person is watching and swapping and so forth, rather than, oh, I will implement that phase and I will implement the other phase, because, of course, when it comes to exam time, if you didn't implement that sort of second phase, it gets, harder, right? And I don't want to have to say this again, everyone understands this, but, yeah. Okay. So let's see if I have any notes on that. Okay, so I did load code words yesterday, so I've already seen some people start, submitting their compilers. And also everyone should, so everyone should pick one so we know who's partnered with who, essentially, right? And also, you should use the same code word. I mean, capitalizations and so forth. So I saw that happen, and where one person didn't capitalize anything, and others. And I just assumed that they were actually teammates, because what's the likelihood of them picking the same random word? So I just picked the one with capitalizations or something like that. And that's what you'll need to submit. Okay? Any questions on these logistics and such? Okay. All right. So as far as questions on the submission site, this is what the submission site looks like. Okay. So you enter your name, your code word, and your assignment, the assignment number, and you upload your zip file of your compiler. Right? Remember, you can structure however you want, so we'll just unpack it and compile and invoke compile.py. That's the only sort of input that we get from you. As far as your compiler submission, when you submit, you'll get a report of how many grader tests you pass, and then the tests, the sort of user-contributed tests. Okay. And so you can do that, and it's open now. The one note to repeat from the Piazza and from a couple days ago is that the tests are not open until the last day. So, so there are links there in that sort of report. Those links will be broken until the last day. And the last day, those links will magically start working again. All right? Okay, and that's again to sort of make sure that you're sort of doing your test-driven development for your compiler, and it's sort of a balance, right? I feel it's too cruel and unusual punishment to not give the grading tests out only sort of in final submission time after you submitted everything or something. So that's why I sort of give it in the last day. Like normal courses where they just grade you after you submitted, right? Okay, so this other page is for you to submit your tests. Okay, so when you submit your test here, then your test will be run against all the previously submitted compilers for the assignment. So remember, we have this little competition on who can build the hardened compiler and who can build the most devious test case, or give the most devious test case, and help each other flesh out those bugs from the compiler. So Drew, question?
I saw in the Piazza that we don't have to support variables like x equals input and then print x plus 5.
No. You do.
You do?
Yeah.
Okay.
Variable assignment printing, and then like basic adding arithmetic.
Okay. We can talk about that in more detail here in a moment.
Do we need to accept an input or an argument to the input function?
No, just empty input. So no prompt, nothing. Yeah. Okay, so just take integer input. That's the only thing you need to worry about. Okay, so then there's the leaderboard that shows this. So let me reload and make sure. So we already have some submitters and some very hardy compilers already with, you'll see that there are already a lot of tests here. I thought we would, have a little bit more fun of competing with, compiler students of past, the ghosts of compiler students, of previous compiler students. So that's why there's already a bunch of user-contributed tests. I presume, maybe some of you have already submitted some, but I presume most of these tests are the ghosts of compiler students past. Yes, Alex?
Just a quick question about the input. So you said input, it's not going to take any arguments, but then you said something about integer input.
Yes, okay. So let me emphasize here. Let's see if I can make this bigger. Right. So each test consists of 2 files.
Yeah.
They should have the same name. So, foobar test 1. No, maybe something more descriptive than that. With the py extension, that's the Python program to compile.
Yeah.
Okay. And a .in, which is the list of integer inputs for your program. So when the Python program has an input,
Yeah, it waits.
right?
Your unit.
then it's going to take in an integer, right? And what we're going to do is just pass your in file as the input file.
I guess we should do it. Keep this separate.
But
I think that makes sense to me. Okay.
right. So normally, if you were to run your Python program, input would just halt and wait at the terminal.
Oh, okay.
But can take input from standard in, and that's how we're going to.
Okay.
So of course, make sure that your tests are well formed, right? Like if you take 3, input, your execution will take 3 inputs, then your list has at least 3 inputs.
So do you do it as like a bunch of separate input files? Because I was just having one large one with more than you need necessarily.
You can do that, and you can submit that as your tricky test case if you want.
Okay.
Certainly from a test-driven development standpoint, it would sort of encourage sort of having the suite of test cases so you could sort of build up.
Well, I've got separate test cases, but I just have one data file. I don't have separate ones for each test.
That's totally fine, but just when you upload here, your set of test cases, just do one each. Or just duplicate your in file, however many times for this sort of submission process. All right. So it is like the most primitive interface, right? Essentially we're supporting anything, however you want to architect your software is totally fine, and that's why our interface is as primitive as it is, if you will, or as simplistic as it is. Okay. All right, let's see, what other questions did come up on Piazza? Why? It's always strange. Let's see, okay. Couple questions that came on Piazza, right? So, do we need to sort of do optimizations and make fantastic code? No. Okay, right. Start off, just make the most straightforward compilation. Right? So translate to your flattened AST and generate essentially one instruction for each flattened statement, more or less one instruction. A few extra, and then header and so forth. Okay, so don't worry about this. About optimizations. You, of course, are welcome to, right? Your code will still be judged correct. If you're sort of, oh, I'm bored, I'm done, I want to tweak my compiler, you're welcome to do things, but don't make that a primary concern. Right. The question about, what's internal compiler representation? What's the sort of suggested way to structure your data structures internally in the compiler? So by flat ASTs, what do I mean? Or, the flattened intermediate language, what do I mean?
Yeah. I would like it's just like an unrolled AST. It's not recursive.
Right. Is it the string temp equals 45? Mm-hmm. Yeah. What is it? It's using the Python.
The function names and stuff.
Yeah, it's still using, the Python, assign or something, if I recall correctly, something like this, right? Those objects. So, Luke, right? Mm-hmm. All right. Okay, that's definitely the suggested, you could probably make it work for this assignment using internal strings, but, you'll have pain in the future. I guarantee it, sort of thing. Okay, Alex?
Okay, and so basically what you mean by that is that you're basically only going to be looking at the AST nodes that sort of that are simple expressions, like assign, that don't have children.
That's right. So you're going to normalize. So at first you're going to have AST nodes that's an arbitrary depth tree.
Yeah.
You're going to normalize it into a set of, a list.
Basically a list of AST nodes
right.
that are represent each sort of part of the.
That's right.
Your temporary. Okay.
So I'll put this as a question here to discuss more flat ASTs. I just wanted to give first an overview of the Piazza questions, and then we'll organize. Okay, so the internal compiler representation. Okay, so there are some questions about Linux, Windows differences, and in fact you'll find similar things if you're using Mac OS. Now, the important thing is that the testing machine is a Linux machine, so your default compiler should support, a Linux machine. And there was this post, I forgot who posted, but, having underscores and non-underscores. If you want to test on your Windows machine or your Mac, that's totally fine. Just know that there are differences and, have some command line flag that switches between the two, and make sure your default one is output Linux stuff. Or for simplicity, install a VM or something, or use the computer science VM to have a Linux setup. Okay?
I have a question. So we are following the two-step process that you mentioned, and the first step was to convert the given AST into a flattened AST.
Right.
And the second step was to convert the flattened flattened Python AST into a flattened x86 AST.
Mm-hmm.
How do we do that? Because do we have a given set of AST nodes for x86?
No.
So do we have to come up with those nodes ourselves? Or?
So I would totally suggest to develop your set of AST nodes for x86.
Okay.
It's definitely my strong recommendation, right? So, you'll have you can use the existing Python ASTs for your flat ASTs. That's no problem, right? And then a set of classes that you develop and you decide. So you can name them whatever you want, right? It's all your internal representation, right? But I definitely suggest that. Again, of course, I've seen many compilers in past, and people just decide to use strings for their x86, and it becomes quite challenging, right? So it is, or at some point they refactor through the middle of the semester or something. But right now, you could just go ahead and develop the x86 AST nodes or IL that you need, and then write a little printer from that to string, which is your final step, right? So you want to make the sort of your use of strings kind of minimal. Right? Only sort of in the input, you parse, immediately get into a data structure in AST, and then the final step is to print from the x86. Yeah, excellent question. Kyle?
So would you suggest that we have like a one-to-one mapping from an x86 node to one instruction in x86?
Yes.
Okay.
Now, I wouldn't worry about developing it for the whole instruction set, just for the ones that you need for this project, and you'll extend it through the course of the semester.
So we just have to build a new tree with x86 nodes, given that we have the Python flattened AST.
That's right.
Okay.
And so the goal here in a compiler is actually, the whole process of a compiler in general is actually rather complex, but you break it down into small phases, right? So we typically think of a compiler as a pipeline, essentially translating from one language to the other, like over and over, right? This is the sort of, this is the picture we always have in our head of a compiler, is that, yes, we have, our strings here in one language, in string, in, language 2, and a compiler is a whole bunch of boxes doing very relatively simple things in each box, but together do something, quite complex. More or less, this is the structure of every compiler out there. And in here you have various intermediate languages. And when I say intermediate languages, inside the compiler, these are ASTs. Okay. Okay, excellent.
Wait, can I ask one more question about
Sure,
that?
yes.
So when we're looking at making the x86 AST classes, so I know you can sort of dig into Python and you can see exactly their implementation of, is that good to use as a model, or
Yeah,
is it going to be?
that's fine implementation.
Okay.
So essentially what we have in the notes shows you can dig into, of course, the actual implementation in Python.
Uh-huh.
Okay, of these AST classes for the Python ASTs, for P0 ASTs that we care about, right? Something like this is probably what you want for your x86.
And then since we're looking at flattened Python code, I guess I haven't thought too much about this yet, but when I'm looking at making an x86 AST, is it going to have a tree properties, or is it going to?
No.
It'll be it's going to be a list where I'm going to basically
Yes, so you're going to have a list of instructions, right?
Okay.
In fact, you could, I mean, you're not going to be able to enforce this with any typing because, of course, Python is dynamically typed. But, you should, your instructions, you'll have a list of instructions. You'll have a bunch of classes that represent different instructions.
Okay.
Or you can structure it with some various different opcodes. Again, this is totally up to you. And you'll end up with a list of those instructions.
Okay.
And so you'll probably have a node or some way to represent the list, like the statement. The statement class here, the statement node is just takes as input a list of statements. Okay. So however you want to design it and structure it is completely up to you. But I definitely suggest some set of AST classes like this. Okay. Right. Okay, I think that's good as far as main questions. Right, and of course, I think there was one more question of, related to this issue. From the Piazza is, how do you test something here in the middle here? Like you do some translation, a couple steps or something, and you want to say like, I don't, maybe I'm not, I don't trust this part of my pipeline, and I want to make sure that the front part of my pipeline is good. Miles?
Print it out? Yeah.
Okay, Miles?
Yep.
Okay, so what are the ways to test?
Print it out.
Okay, so you can print it out and read it. Right, so it's hard to actually, you could just dump the ASTs, right? We've looked at some of those representations, right? Those get kind of hard to read. So we might implement, a pretty printer. This is what it's called. What does that do? That converts abstract syntax to concrete syntax. So typical things we have for every language is we have a way to read from concrete syntax to abstract syntax. What's that called? Parser, right? Okay. And then a way to go from abstract syntax to concrete syntax is what's called a pretty printer. Okay. So we might want to implement such a thing so we can sort of dump it and read it more easily. For sure we need a pretty printer for x86 ASTs because we do need to output that, right? So, there's no way around that. Miles?
Could we export a .dot file, use GraphViz to actually...
Yeah, if you have something graphical to visualize, of course, yes. However you want, right? Yes.
Write a test suite for each step.
Okay, so test suite for each step. How are we going to test the semantics? So what's the semantics of a programming language? It's meaning, okay, and what is that? What it does, right? How it evaluates, how it executes. So we might want to write, so test execution. So we might want to develop an evaluator. Right, so we can develop interpreters for our little intermediate languages. Right, so we could check that we have the Python interpreter for our source. We have our x86 machine. We can run to see their results. We might want to run some intermediate step. We might want to run, our x86 ASTs. We might, through our interpreter rather than the printing, although that's probably less crucial. But we might want to have a little interpreter for our Python ASTs so that we can actually test our, the intermediate. For example, our flat ASTs. We want to make sure our flat ASTs have the same meaning as the input Python program. How do we do that? Well, we have to run our flat AST some way. Right? So this is, of course, code that doesn't end up in your compiler, but it is part of the whole compiler development process. Okay. All right. So if you invest a little bit in time in this, and then, it will be, if you're finding you have, I know it's very hard, when you're thinking about, well, my deliverable for the homework is that compiler, so I can't spend time developing this, evaluator or something for my intermediate language. But I promise you that will be sort of weight in gold as you move forward. Okay. Right. Okay. So that's good. So let me rewrite up there. So about flat ASTs. Other questions? So now I'll turn to you. Let me get your list of questions so we know what we need to talk about today. Okay, Andrew?
What's the GCC command to actually compile the assembly code? I tried doing the one that you gave last time, and I kept on getting linker errors.
Okay, let's.
The .c file. You actually have to compile
the .c file.
To .a or .o.
Oh, okay. All right.
Because it relies on a bunch of other files, so you can't just use the .c.
Well, yeah, but I mean, okay. You mean you don't have to go compile the? Well, okay. Let's talk about that in a moment here. Let me get all your questions. Nothing else? We're set. Okay, for now. Okay, Alex?
Can we just talk a little bit about x86 code? I don't even know if I have specific questions, but as someone who has never done any x86 code, maybe just the important stuff that I should start to look at, or go through a small example with.
That's a good question. I was hoping that question would come up, Nilesh.
So for this assignment, can I assume a call from this always a print statement?
Yes. Yeah, so not print, but input.
Oh, sorry, yeah.
Okay. All right. Let's see if I have written down exactly the command. Let's make sure I get it right. The process. Thought I had it written down, so. Okay, so what is our process? So what is the auto tester going to do? It's going to run Python, I guess Python 2, your compile.py of, test.py. Okay, and then your compiler is going to end up with a test.s, okay, which is your x86 assembly.
Quick question on Python 2. Do you have a specific subversion?
I think we're just using the newest 2.7 something.
Okay.
On Linux. I can double check that.
Because 2.7 has a wider command set than 2.5.
This is true. So you are welcome to program in 2.7. Okay. Okay. And then what we're going to run, we're going to say GCC, dash M32, whatever, start.c files for the runtime, and, dash o test or something, right? And with your test.s. Sorry. So, or you can build them to object files or whatever first. It doesn't really matter. GCC will take care of it and give you your executable.
Should have LM.
Huh? Oh, the NLM, you're right. So let me just emphasize it's executable and steal some Windows stuff. Right, so test.exe or whatever, and -lm for the math library, right, that the runtime uses. Thank you. Okay? And then we're going to cat test.in to run test.exe. Okay? And then it's going to print out some stuff, and that's going to be the result of your executable. So yeah, bare bones computation from, the 70s or something earlier, right? Nothing fancy, right? But that's the kind of program we care about, right? For this class, right? We don't care about the input programs, we care about developing our compiler. Yeah, so I don't think, P0 is an effective programming language to be, developing your web servers or anything. All right. Questions on that? Andrew, does that answer your question?
Yeah. Thank you.
Now, the M32, of course, is only if you're running on a 64-bit machine, although I guess pretty much everyone is these days, so. Okay, so let's look at x86 a bit, and then we can go back and talk about flat ASTs, since I think we talked about flat ASTs some already. All right, so maybe it's best to go, okay, to the notes. Okay. Is this the simplest one? Okay, so first thing we look, this is essentially some bit of x86. That's x86 assembly code for this example program. X gets assigned negative minus input, and then print x plus input. Okay. First thing is like, what are all these percent things? Percent EBP.
Registers.
Okay, these are registers. Okay, so percent EBP is a register. Let's see, I have my list of all the registers, right? So because it's x86, there are like only 6 or something like that. Percent EAX, percent EBX, percent ECX, percent EDX, percent ESI, percent EDI, and then EBP as a head, and percent ESP. Okay, and they do have, by convention, particular uses, right? They're just, a register is what? Just a chunk of memory, right? It's 32 bits, on a 32-bit machine. You can think of it as a box or a variable that you could put 32 bits of stuff in, right? All right, but by convention, we use particular ones for certain things. So what's EBP? Sam?
The frame pointer.
Yes, okay, so the BEP stands for base pointer, but, the other terminology is frame pointer. Okay, and what's ESP?
Stack.
The stack pointer. Okay, so that's what it stands for. So what's the purpose of these two? Okay, Sam?
Basically, each function kind of has its own frame on the stack, so you sort of use the frame pointer to, when you're done with one function, if one function calls another one, it's just used to sort of figure out where it goes back to.
That's right. So, so the frame, or sometimes called the activation record, what is that? That represents the local variables of the top of the current function, the current activation, right? The current function that you're running, right? And so, we have our stack. Remember your systems course, right? The stack kind of goes down. And then, so the topmost frame of the stack is maybe this region, right? So this is the topmost activation. Where does the stack pointer point?
Very bottom.
The very bottom. So the stack pointer tells you where the end of the stack is. Okay. And what is where is the base pointer point?
Beginning of your activation.
The beginning of your activation. Okay. So the base pointer or frame pointer and the stack pointer delineate your topmost activation. Okay. Good. All right. So
Wait, what do you mean by activation?
All right. So let's answer Alex's question. What do I mean by activation?
A function call.
When I make a function call, I need a place to store the set of local variables
Okay, so
for that
it's
function
the
call.
local variables then.
It's the local variables. Well, or your stack may store other things. But when I say activation, really mean an instance of a function, right? A function call has some chunk of memory that represents that function call. So I think an activation is kind of synonymous to, a function call in a sense. Okay. I lost my place here, my notes here. Ah, there it is. Okay, so, right. Huh?
So now when I push something onto the stack, only the stack pointer changes or both the base pointer and the stack pointer changes?
Okay, so that depends what you mean. So let's answer Alok's question, right? If I want to sort of allocate a region for my activation, right, which one am I changing? Okay, so if I'm allocating a new activation, I'm going to change both. Because I'm going to, if I, allocate a new activation, I'm going to take a new chunk. So let me pick a different color here. For my next activation. And I'm going to switch and I'm going to have EBP be here. Okay. And that's, in fact, the job at the beginning of a function call, is to allocate a new activation. Okay, so in fact, we can actually see that code right here. Right, so this is a bit of code that is a little bit of a preamble that you're going to have at every function. And what is its job? So what is it doing? So what does push L do?
Pushes the current EBP to the stack.
That's right. So in the first location of my new activation, I'm going to store this old EBP. Okay, that's the first step, and then I'm going to move ESP to EBP. Okay, so one thing to get used to, this is AT&T syntax. The destination is on the right. Okay, so the thing I'm writing to in this move is EBP. So I'm going to change EBP to point to the current ESP. So I guess it's kind of really the same place. And that will be my new base pointer. Delineate. And the stack pointer points to the bottommost activation. And this is sort of moving the stack pointer down. So sub L4 here says move 4 bytes down. So allocate, a cell, a cell, I guess, on the stack in this activation. Okay, so that's what's going to move the ESP down. Okay, so these first 3 steps is save the old EBP. Okay, as the first slot. Okay, now move the EBP down to be the frame pointer for the new activation, and then allocate a cell for this activation. So this particular activation just has 2 cells, right? One for the old EBP and one thing that's reserved here. Okay. All right. Let's see. All right. So what other conventions are common here? Well, so EAX is used what?
Return value.
For the return value. Okay. One question I forgot to ask in this last discussion. Why do we save the old EBP?
Because you got to know where to go back to.
Exactly. So when I'm done with this particular activation, I want to kill this piece, right? This red piece. I got to know where to restore that EBP to be, this blue place again, right? once I kill this, I have to go back to here, right? Okay. Okay. So where's that done in this code?
At the return.
Yeah. Leave, return. Okay, so leave is a little bit of a macro that, because it's, x86 or whatever, that really just says move L EBP to ESP. Okay, and then pop L EBP. Okay, so that's what leave does. It's the inverse of the push and move. Now, why isn't there like a, enter sort of macro instruction? Well, I don't know. Nico?
Would it be move L EBP? Is that what you said? Or is it EDP?
EBP.
Okay.
So I want to take the base pointer, the current base pointer, and make that the stack pointer. So I guess my diagram, I should be a little bit more clear here. The EBP is actually pointing just above what we consider the activation, right? So, okay. Right, so we're writing the current EBP into the current base pointer into the stack pointer. That's moving it back up to this point. The stack pointer back up to that point. The last cell of the previous activation. Okay. And then we are taking this last node of the EBP and storing that into EBP. The old EBP that we stored on the stack. We are restoring it. It feels like, and whenever I talk about assembly, I just feel like I'm talking in circles because it gets so low level. So,
what does POP-L do?
POP-L, okay, so POP-L is going to take this. So I make sure that my stack pointer is pointing here.
Okay.
Okay, and then I'm going to take the last cell and store it into EBP. Right. So remember, the last argument to any instruction is the thing that you're writing to. That's the x86 or the AT&T syntax convention here, right? So here we're writing to ESP, the current contents of EBP. Here we're taking the top stack element and writing it to EBP.
So it is implicit that it takes the top stack element.
That's right. That's what POP-L is doing. As determined by what? Which register?
ESP.
ESP. Okay. All right. So this is kind of, messy and so forth. But it just takes at least one time in our lives we should sort of execute and understand the x86. So I'm going to have you guys get, with your partners here and, take 10 minutes to work through this example, trying to write out how all the components of this little Python program go through this, generate this code. Right. And I sort of got you started with the preamble part.
This is pretty literally. Those and I am going to know. Well, this is a speed generator. This is going 2 layers down. This is that is 2,000. The stack goes down. Pointing 4,000 here. Okay, why are we? As far as that goes back to here, I need to. Yeah. Red. Go back like 90 pictures or about that, but never done it.
I got that. Yeah,
Did you get these though? The nice thing is you can
I do just had double quotes?
I like this one. It's like this or something, but there's also I go down to like those I usually
Oh, here. Bye.
pretty nice.
Yes, exactly. I do it like this.
Otherwise, you'll get a non.
I should name myself as back up all my notes. All my textbooks here too.
Oh, I think it just says versus.
Right, close it down.
It's worth it.
That way it winds back
That's
up.
like most of my problems. Like I text one letter and
You guys want to talk about this?
What's that?
oh wait, no, that's not right. That's not.
So,
They just.
I mean, it doesn't have to be your, project partner. Talk to someone about this.
Exactly where we're
Want to go back to the
gotta be drawn pictures.
Sure.
I called it.
Yeah, so that's vision. That's just negation. Okay.
You guys are already done. You're a week in advance. Awesome.
Now we're trying to make
Cool. Remind me your names again. This one's going to take us several times. Nick? Josh?
So I've had
Yeah, my
That's why you don't need to set up any phone. To get the stack pointer in the right place, you allocate the cells.
Stands for that this person put it.
But, well, no, like, I mean, you want to sort of make sure your stack pointer is always, like, in the right place for your sort of sanity in your compiler, even though this is, in some sense, doing extra work. Go in and finish and optimize and so forth. But you're gonna, when you're doing your code generation, you're gonna say, okay, this is my code to set up, and this is my code to tear down, right? And then each flattened instruction is going to correspond to, what a set of these instructions. So it's simpler if you sort of have things sort of very regular. What? So the add L is probably to essentially, the add L is part of that call to print. Because it's going to push L, there's a push L, EAX, for the argument to print, and the tear down of that new cell is going to be that add L. So you're going to have a call to print, and it's going to actually generate those three instructions, the push L, the call, and the add L. So it looks weird, right, because now it just returns at the very end. But you can imagine doing many other things after the No. Which other function? You don't have to worry about. Now, of course, if you did a little bit more analysis of your function, you could sort of allocate everything you need for the function and not have those sort of allocations in between, and that's not the foundation. Right. Once you have such flexibility at the low levelness of the assembly code, there's so many ways to generate code, and having a fast compiler and optimizing compiler is one that minimizes the impact of operation. Right.
I guess it really depends on how well it's probably just
We allocated those 4 bytes. I think we're 4 bytes.
Exactly.
I guess the tree will end up being
So that's what we've called
Go from the AST one.
Well, your best.
Where do you put that?
Yeah, like
I'll make it now.
and that's what we're thinking.
So I started to allocate the
The percentage?
Yeah. Right now we're so we had a frame, like we had a frame.
I don't think so. All right. Let me bring you guys back.
Did you mean tab
And work through this together. Some good questions that came up that maybe we'll see as we work through. Okay, so let's see. Where am I at in the picture? I guess I'm at the picture where we're at this point that we finished discussing. All right, and I was just thinking very carefully about, I was a little bit sloppy in our previous discussion about, I think we typically think of the activation, again, this is up to you of how to see it, but the activation as including the old EBP. And then in that case, the EBP and ESP sort of delineate within, right, the activation. Of course, it's sort of hard to say, whether that's part of this activation, but anyway. Okay, but from that standpoint, EBP points at the cell that always holds the old EBP. That's 0 EBP. And so we've done this sub L4, so now ESP is point down here, so that's -4 of EBP. Okay. Okay, so what does this first thing do? It calls input. Okay, so what is input going to do? So this is some part of our runtime. We know from the calling convention, it's supposed to put what?
It's return value in EAX.
It's return value in EAX, right? So in EAX, we have the return value from input. Okay, right? So that's, if you will, we've sort of done this part. We've called input. Okay, and the next instruction does negates it, right? So here we're sort of, after we're at this point, we're sort of done the neg L here. So let me make this our program cursor. We've done this part. So this is kind of the neg L part. Okay, so what's the next thing doing?
Storing the value.
Yeah, so it's storing EAX into the stack, which is this, our sort of minus input. So, or actually really this X, right? This X variable in our Python program, which is minus input. Why is that? Why do we need to do that?
Because EAX is going to be used when we're calling input again.
Yeah, exactly. It's going to be like destroyed at this next call, when we do this next call, because it's going to write its return value into EAX. Right? So if we didn't save it, then it's just going to get blown away. Okay. So I guess this is a good segue to talk about call ESAVE and caller save registers. Okay. So this is using the cdecl calling convention. Right? So this is part of the calling convention. When we do a call, there are certain registers that should be saved by different parties, right? That's essentially what this is. So call ESAVEs are which ones? Or who's responsible for saving them?
The function called.
The function that's called, right? So that means when I call input, like, I know that certain registers are not going to be touched. Does anyone happen to know which ones they are? Yeah. Right. Let me make sure I don't mess this up. And give the wrong information about that. Yes. Okay, so the caller saves are EAX, ECX, and EDX. So this is the caller. This is not legible this way. So caller save are EAX, ECX, and EDX. Okay? And then the remaining ones are call ESAVE. Okay? So if input wants to use like ESI in its code, which it's free to use, it's responsible for saving the old value and restoring it before it returns. Now, EAX is a caller save register, so input is free to blow it away and do whatever it wants with that register. If we want to save that value, we have to save it. And that's exactly what we did. We saved it. Okay, we, the caller here, this outer context. Right? All right. So I guess we've done the call. So now in EAX, we have the second input. So we're kind of, up to here. We've done that input. Okay. So what's the next instruction doing? Yes,
I have a
Alex?
question about for saving them. So we know that so do you always have to, we have to save it because we know we need it later, right? But
Yeah.
So do you just always save it? Can you ever know that you don't need it later?
Okay. So how could we know that we don't need that value later?
If you haven't used it, or
Okay, so if you haven't used that register, yes. But if we've used it, like in this case for EAX, then we need to know that in the rest of our Python program, we don't need that value anymore. Which we could with some program analysis, right, to figure out, if we need that value, potentially, right? But for simplicity in this particular project, we might just decide if we've, used it and, we want to say we might need that value, we just go ahead and save it. So I think this question came up here, right? You know, in this code itself, right, there's redundancy that's like, if you sort of look at it from a human being standpoint, as we're doing now very carefully, there's redundant computation here that can be optimized. And an optimizing compiler was going to work very hard to sort of reduce the additional computation that's not needed. Why is this code like this? Is because it's somehow a very direct translation of every sort of Python statement, every flattened Python statement.
Question.
Yes.
Is there a reason that you're not using general purpose registers to just store the accumulator value and everything?
I was going to ask that.
Yes, because I want to generate simple code, and I don't want to have to worry about, if I run out of registers or things like that. In fact, in this assignment, we're going to use the stack for all our local variables. So in some sense, I've decided that -4 EBP is going to be my x variable.
Just push and pop takes more time than just...
Yes, absolutely. No, again, no doubt about that, right? That using the stack costs more, but stack is a sort of unlimited variable store, which is very close to what we have in Python. At least conceptually, the stack is unlimited variable store. We can use that. And so essentially, I'm going to build up this map saying that my x variable from this program is going to correspond to -4 EBP, and I'm just going to use that, basically for everything.
Yeah, I understand.
Right. And this is simple code generation. Okay. And then it's another step to figure out how do I use registers. And this is actually a process. And actually, the most important optimization in any compiler is doing register allocation, which is homework 3. Right. So, absolutely. This is not fast code. This is what we would say, what do we have in our first day talking about bootstrapping? This is really writing our sort of crawling compiler, right? This is not generating optimal code, for sure. Okay. So, all right. So, in fact, what we do is the next instruction is this add. And you can see we've decided this. We're just going to add from the stack the location that stores x. So there's a very direct correspondence, right? That this is -4 EBP. Oh, and this is the addressing expression. So -4 EBP. Right, is a way to read in memory. So dereference the pointer that's stored in EBP and subtract 4 from it. That's the pointer. Okay. So this is called an addressing expression, I guess. x86. Right, so I totally will probably have this maps, some dictionary in my compiler mapping that x corresponds to -4. Right? And that's, or something like this. Just to, and then that's how I'm going to do my code generation. Okay? So this add L is just going to be this add of this return value of input in X. Okay? So I guess we are here. All right. Now what? Yeah, so we're going to push that new value to the stack. That new value, what is the new value? It's actually this addition. So the add, I should mention, right? So the destination is always on the right. So we're writing to EAX. What are we writing?
The addition of EAX and
yes. So the addition of EAX and EX, right? So we think of add as like a 3-place thing, right? It takes 2 inputs, returns 1 output, right? The 2 inputs are actually those 2 registers, EAX and -4 EBP, and we write to one of those registers. So the yuckiness, low levelness, right, is we have to realize that EX is both being read and written to in that add. Okay. So which sequence of instructions do you think correspond to the print, right? In my simple code generator, I'm going to say, this one flat AST corresponds to what instructions of print?
Pushing the EAX and the calling
Yes. And this was surprising a little bit as I walked around to some folks, that this is the code generation for print. So what's the push-L doing?
Putting the argument for print on there.
Putting the argument for print on it. So the arguments are read off the stack. That's the calling convention. So the arguments to functions, we didn't have to think about that for input because it took no arguments. But the arguments are put on the stack. So what I'm going to do is write, I guess, so this will be at the -8 point. I'm going to tack on a new cell of, so this would corresponds to x plus input. Okay, and then that's going to be passed to print. I'm going to call print. So in fact, the stack pointer with the push moves down. Okay. Okay. With the push, I call print, and then what do I want to do now? So what is the addl doing?
You're jumping back to the stack pointer to go.
Yeah, it's putting the stack pointer back up. Right? So it's like, oh, I actually want to kill this cell. Right? And make the stack pointer back to my sort of standard activation. Right? So I did an allocation just for the call, and I want to sort of put it back. Right? It's sort of stealing space from the allocation. Now, of course, this is not, optimal necessarily, right? If you knew you were going to need that cell, well, I should just allocate it at the beginning, right? And then I'll just deallocate at the end. And in fact, the question that came up is like, what looked weird is like, well, why are you changing the stack pointer when immediately here, down here, you're writing to the stack pointer without really reading from it again, right? And leave, we are writing EBP to ESP. Right? So that add is kind of redundant. Well, in fact, it is redundant. I shouldn't say it's kind of redundant. It, in fact, is redundant. It's wasted computation. Right? So an optimizing compiler would say, well, I don't want to do that. I want to not, write that instruction. But, from the perspective of simple code generation, I may do lots of other things, and I want to make sure my ESP is in the place I expect it to be. So I'm just going to always make sure my ESP is sort of pointed at the bottom of my activation. Okay. And I don't have to worry about, what goes on, later. Okay.
I have a question.
Yeah.
When you call the print underscore int underscore NL, doesn't that anyway create a new activation and change the...
Oh, yeah. So it's going to create its own activation. And it's going to change the ESP, but it's going to return ESP to where it was before the call.
So isn't that doubly redundant then?
Well, it's going to end up, the ESP is going to maybe move down to down here or something. Right? And then when print restores, it's going to go back to here. And then we want to clean up that little spot.
Okay.
Right? So, yes. This is all sort of because, you have to have conventions because, otherwise, you have no idea what it's going to do with your registers.
Redundant.
Yeah. Nico?
Couldn't EAX get overridden?
EX will be overwritten by print. Oh, could be written by print, yes. So we aren't using EAX, right?
Okay.
EX is a color save register, so, if we needed to save the value that's currently in EAX when we call print, we would need to save it. Okay. So the final bit is to set our return value, so we return 0. So that's this bit, right? And then leave ret is the part to restore the base pointer and stack pointer to the previous activation, and then to jump to the return address.
Don't we have to save the return value on the stack somewhere?
Where does the return value go? EAX, and that's here.
No, but
move L.
Isn't it the first? So the first entry in any in the activation record of a function, isn't it the return value?
Not the return value. The return address. And that's what ret is doing, is using that, is dealing with the return address.
So it will use these 3 registers to give the return value.
Okay, so the return value is always saved in EAX for every function. That's the convention. Arguments are on the stack, right? And EBP and ESP delineate the activation record. Okay.
I'm not sure it matters, but what do we do if the function's void? What do we put in EAX, or do we just leave it as is?
So you're going to decide upon some conventions here. I think here we're just returning 0 because it's main.
Yeah.
So you could not do anything with EAX, whatever. Okay, so it looks like it's 10:45. So it's been a pleasure. Good luck. Bring your questions for the final day on Thursday.
So that